Hello and welcome to the show. Before we get started today, I want to make sure we state very clearly that the review you're about to hear was generated by artificial intelligence.
It is a pleasure to be here.
Today we're going to be analyzing the book Learning SQL by Alan Beaulieu. We're looking at the second edition, which was published by O'Reilly.
And this is really a foundational resource. It goes beyond just the syntax, the commands, and gets into how databases actually work with the standard query language, or SQL.
That's right. And this discussion is definitely intended for a more technical audience, for anyone interested in the engineering behind relational databases.
We're going to be taking it chapter by chapter.
Exactly. We'll analyze it one by one, focusing only on the useful technical concepts that matter to developers. So let's start with Chapter 1, a little background. It talks about the history of data storage. Why is it so important for us to understand that shift from, paper to computers?
Well, it's all about context. It explains why the relational model was even invented. We started with paper files, which, as you can imagine, was very slow.
Incredibly slow.
Then we got early computerized databases. But the problem was they used physical pointers. So to link a customer to an order, there was a literal link on the disk.
And that sounds fragile.
It was very brittle. If you changed the physical data structure even a little bit, the program that read the data would just crash.
A complete maintenance nightmare. So the book brings up Dr. E.F. Codd and his 1970 paper. How did his work solve this pointer problem?
Dr. Codd's idea, the relational model, was truly revolutionary. He suggested we get rid of physical pointers altogether. Instead, all data should be represented in tables.
Just simple tables.
And to link those tables, you use what he called redundant data. So you store a common value, maybe a customer ID number, in two different tables. That creates a logical link, not a physical one.
I see. So the database can find connections without caring where the data is physically on the disk.
Precisely. That leads us to the key terms in the chapter, like entity, column, and row. You asked about the difference between a primary key and a foreign key.
Yes. Could you clarify that distinction?
Of course. A primary key is a rule, a constraint, that makes sure every row is unique. Think of a user ID. No two users can have the same ID.
Okay, that's the unique identifier.
And the foreign key is that redundant data I mentioned. It's a column in one table that points back to the primary key of another table. The foreign key is what actually builds the relationship.
The book also says SQL is a non-procedural language. For programmers used to languages like Java or C, that's a big shift. What does that mean in practice?
It's a fundamental difference. In a procedural language, you tell the computer how to do something, step by step. Go here, open this, read that.
You write the recipe.
Exactly. With SQL, you only declare what you want. You don't specify the steps. That job belongs to a component in the database called the optimizer.
So you just state the goal, and the optimizer figures out the best way to achieve it.
It does. It looks at your request and decides the most efficient path. Whether that's using an index or scanning a whole table, you delegate the how to the database engine.
A crucial concept. Okay, let's move to Chapter 2, Creating and Populating a Database. The book's examples use MySQL, specifically version 6.0.
That's right. And when designing tables, you have to choose your data types. The book makes a good comparison between char and varchar.
Why should a developer really care about the difference?
It comes down to efficiency, both for storage and performance. Char is a fixed-length string. If you set a column to char 20, it always uses 20 bytes of space.
Even if you just store the word hi?
Even then, it pads the rest with empty space. Varchar is variable length. It only uses the space it needs, plus a tiny bit of overhead. So you'd use char for something always the same length, like a two-letter country code.
And varchar for everything else that varies, like names and addresses.
Correct. The chapter then gets into normalization, which can be a tricky topic for beginners.
So what's the core engineering reason for normalization?
The main goal is to prevent data errors that come from storing the same information in multiple places. Imagine you store a customer's email address with every single order they make.
Okay, so hundreds of times for a good customer.
And then they change their email. You would have to find and update every single one of those hundreds of records. If you miss just one, your data is now inconsistent.
I see. So normalization says you store that email in one place and one place only.
Exactly. In the customer table, the order table just holds the customer ID. It ensures data integrity.
That makes perfect sense. Now, on to Chapter 3, the query primer. This is all about the select statement. You mentioned the optimizer. What technically happens when a query is sent to the database?
It's quite a process. First, security. The database checks if you even have permission. Then, your query goes to the parser, which checks your syntax.
Make sure the SQL is written correctly.
After that, the optimizer creates its execution plan, looking at all the available indexes and statistics. Finally, the engine runs that plan and sends back what we call the result set.
The chapter lists the main clauses: select, from, where, group by, having, and order by. But it makes a key point that the order we write them in isn't the order they run in.
This is a very important technical detail. You see, we write select first, but the database actually processes the from clause first. It has to know which tables it's working with.
Before it does anything else.
Then it applies the where filters to get rid of rows it doesn't need. The select clause, which picks the columns, happens much later in the process.
And that explains why you can't use a column alias from your select list down in your where clause.
Precisely. When the where clause is running, the database has no idea that alias even exists yet.
That's a great tip for troubleshooting. Let's look at Chapter 4, filtering. This is where we use the where clause. The book spends a lot of time on NL values. Why is NL so tricky for developers?
The problem with NL is that it doesn't mean zero or an empty string. It means unknown. It's a lack of a value.
A complete absence of information.
And because it's unknown, normal logic doesn't work.
Yeah.
If you ask, is this NL value equal to 5? The answer isn't no. The answer is, I don't know. It's unknown.
So you can't use the equal sign.
You can't. If you write where my column in allo, you will get 0 results because nothing is ever equal to unknown. You must use the special phrase is unnel.
A very common mistake to make. Okay, Chapter 5, querying multiple tables. We've normalized our data and now we have to join it back together. The book really pushes the ANSI SQL 92 syntax for joins. Why is that?
Well, the older way of doing joins was a bit dangerous. You'd list all your tables in the from clause, and then you put all your linking conditions in the where clause.
What was the danger there?
If you forgot one of those linking conditions in the where clause, you'd get what's called a Cartesian product.
Yeah.
Every row from the first table would be combined with every row from the second.
So you could accidentally generate a massive, meaningless result set.
Huge. The modern ANSI syntax with join and on separates the logic. The join on part is for connecting tables, and the where part is purely for filtering rows. It's much safer and clearer.
And what about joining 3 or 4 or even more tables? Does the order we list them in matter for performance?
Generally, no. Again, because SQL is declarative, you tell it what you want, and the optimizer figures out the best order to actually read the tables. It might read the smallest table first to filter the data down quickly, regardless of how you wrote the query.
Chapter 6 is working with sets. This is about the mathematical foundations of databases. It covers union and union all. What's the practical difference?
They both combine results from 2 separate queries. The difference is how they handle duplicates. Union will take the 2 lists, combine them, and then do extra work to sort and remove any duplicate rows.
So it's more work for the database.
A lot more work.
Yeah.
Union all just stacks the 2 result sets on top of each other and keeps everything, duplicates included. It's much, much faster. So if you know your data won't have duplicates, you should always try to use union all.
The book also mentions intersect and accept, but it points out a limitation in the version of MySQL it was using.
It does. Intersect gives you only the rows that appear in both query results, and acceptee gives you rows that are in the first query but not in the second. At the time, MySQL 6.0 didn't have these commands built in.
So you had to use other methods, like joins, to get the same result.
Exactly. It's a good reminder that even though SQL is a standard, each database vendor might implement it a little differently.
Let's move to Chapter 7, which covers data manipulation and conversion. It mentions functions for strings, numbers, and especially dates. Why is handling dates singled out as being so complex?
Dates and times, or temporal data, are complex because there are so many ways to write them. You might have year, month, day in one place and day, month, year in another.
And the database needs to understand what you mean.
Right. The database stores dates in its own special internal format. So when you give it a date as a string of text, you have to use conversion functions to tell it exactly how to parse that string. Otherwise, it might get it wrong or just reject the data.
That makes sense. Chapter 8 is grouping and aggregates. This is about finding trends with functions like sum or count. Now, a major point of confusion for many is the difference between the where clause and the having clause.
This is probably the most important concept in the chapter. It's all about when the filtering happens. The where clause filters individual rows before any grouping occurs.
So it works on the raw data.
Yes. The halving clause filters the groups after the aggregation has been calculated. So if you want to see sales data only for the year 2024, that's a where. But if you want to see which sales branches had total sales of over $1 million,
You have to use halving because you're filtering on that calculated total.
exactly. You can't put sum sales in the where clause because when where is running, that sum hasn't been calculated yet.
A very clear distinction. Chapter 9 introduces subqueries, which are queries inside of other queries. The book highlights something called correlated subqueries. What are they, and why are they a performance concern?
A normal subquery runs once, gets a result, and the outer query uses that result. A correlated subquery is different. It actually references a column from the outer query.
So it creates a dependency.
It creates a loop. For every single row processed by the outer query, the inner subquery has to run all over again. If your outer table has 1 million rows, that subquery will run 1 million times.
That sounds incredibly slow.
It can be a major performance killer. They're powerful, but you have to use them with great care.
Okay, chapter 10 is joins revisited. We talked about inner joins, but this chapter brings in outer joins. When would you use an outer join?
An inner join is for finding matches. An outer join is for finding what's missing. For example, say you want a list of all your customers, including the ones who have never ever placed an order.
An inner join wouldn't show those customers at all?
Correct, because there's no matching order. But a left outer join from the customer table to the order table will show you all the customers. For the ones with no orders, the columns for order information will just be filled with NLL.
So it's a way to find records in one table that don't have a match in another.
It is. The chapter also mentions the cross join. This is the Cartesian product we talked about being an error. But sometimes you actually want it, for example, to generate all possible combinations of 2 sets of data.
Interesting. Chapter 11 discusses conditional logic using the case expression. How does this let us transform data?
The case expression is basically if-then-else logic inside your SQL query. It lets you change values on the fly. You could say, turn a status code of 1 into the word active.
But it can do more than that.
Oh, yes. The really powerful technique is using case inside an aggregate function like SUM. This is what the book calls selective aggregation. You can sum up sales, but use a case statement to only include sales from a specific region or for a specific product. It lets you pivot your data, turning rows into columns for reports.
That brings us to chapter 12, transactions. This is about managing data when many users are working at the same time. Why is this so vital for something like a banking system?
Because you risk corrupting your data. Think about transferring money. It's 2 steps. Subtract from account A and add to account B. What if the power goes out right in the middle?
The money is just gone,
Yeah.
subtracted from one but never added to the other.
Exactly. A transaction prevents this by ensuring atomicity. It's one of the ACID properties. It means that group of statements is treated as one single indivisible unit. Either both steps succeed or they both fail together.
And we control that with commit and rollback.
We do. If everything works, you commit to make the changes permanent. If anything goes wrong, you roll back, and the database is returned to the state it was in before you started.
Chapter 13 covers indexes and constraints. We know indexes speed up reading data. Is there any downside to just creating indexes on everything?
Yes, a very significant downside. An index is a separate data structure that stores a sorted copy of your data. This makes reading or select queries very fast.
But it slows down writing.
It does. Every time you insert a new row or update or delete an existing one, the database doesn't just change the table. It has to go and update every single index on that table as well. Too many indexes, and your write performance can become terrible.
So it's a trade-off an engineer has to make. The chapter also touches on constraints.
Constraints are just rules the database enforces to protect data quality. Primary keys and foreign keys are types of constraints. They stop you from, for example, inserting a duplicate user ID or an order for a customer that doesn't exist.
Chapter 14 is about views. What exactly is a view?
A view is like a virtual table. It doesn't actually store any data itself. What it stores is a select query. So when you query the view, the database just runs that stored query for you.
And what would you use that for?
2 main reasons. Security is a big one. You can create a view of an employee table that shows names and departments, but hides the salary column. Then you give people access to the view, not the real table.
I see. And the other reason...
Simplicity. You can hide a really complex 10-table join behind a simple view name. Then your report writers can just query that simple view without needing to understand the complexity underneath.
And finally, chapter 15, metadata. This is data about the data itself.
Correct. The database keeps a record of its own structure. In a special set of tables, often called the information schema, it lists all your table names, all your column names, their data types, and so on.
And this can be used for automation.
It can. A developer can write a script that reads this metadata to understand the database structure, and then that script can automatically generate other SQL code. It's a very powerful tool for what's called dynamic SQL.
We've covered a lot of ground here, from the very history of the relational model all the way to advanced topics like transactions and dynamic SQL. So what is the final assessment?
Learning SQL by Alan Beaulieu is an essential read. It gives you such a strong foundation. It doesn't just show you the commands, it really helps you understand the engineering principles behind them.
So you'd recommend it?
Absolutely. For anyone who truly wants to master relational databases, I would highly recommend reading this book.
Well, that concludes our analysis of learning SQL. We really hope this discussion has helped deepen your understanding of how these powerful systems operate.
We hope it's been useful.
And if you found it useful, please consider subscribing to our show. We wish you a great day.